I'll repeat. Participants, feedback link is already shared in the chat box. You can fill the feedback for this session. For next session, feedback link will be shared during the session. Okay, dear participants, so we'll start with our next session. Our next expert has already joined the session. So we'll be starting our session number 4, EV Dynamics, Handling, Stability and Performance by Dr. Debanand Singh Dev, Senior Customer Success Engineer, MathWorks, Bangalore. A brief introduction about the today's expert. Currently, Sir is working as a senior engineer in the education team at MathWorks India Private Limited, Bangalore. His expertise lies in model-based system engineering workflows for electrification applications. He closely supports academic institutes and startups in projects related to adoption of model-based design in electrical vehicles and renewable energy. He has an interdisciplinary background with bachelor's degree in physics honors, followed by MSc PhD degree from Department of Energy Science and Engineering, IIT Bombay. In previous roles, he has also worked as postdoctoral fellow in the Department of Energy Technology, Denmark, and faculty at Tezpur University, Assam. Equipped with 15 years of action-oriented experience, he has authored over 10 publications in energy system modeling and holds 2 patents. So now request Dr. Debanand Singh Dev sir to start with the session.
Before I get started, just a quick check, you can all hear me fine?
Yes, sir, you're audible.
Okay.
Voice is
Perfect.
clear.
Yes.
So thank you everyone and good evening. Welcome to this session on how you can model electric vehicles.
Hello, sir. Your voice, I think you are on mute. You are audible, but right now you are on mute.
Yes. By mistake, I clicked the wrong icon.
Yeah, we
Okay,
can hear
thank
you.
you.
Yes.
Okay, so a very good evening to all of you. So today we will actually talk about EV dynamics. So this is sort of a very important challenge that all of us sort of face while working on our EV project. So no matter which domain we are from, it is very important that we understand that whatever we are building will actually be tested on a vehicle in the very end, right? So it's very important that we should be able to understand how the performance is affected when you sort of model the vehicle body along with the remaining components of an electric vehicle. Okay, so what we will do today is take some very simple use cases and try to understand how all of this is correlated. So I'm not sure how many of you are exactly teaching this particular subject, but if you are, we would be very happy to also learn from you that what are the things that you're teaching, and we can support you some of the resources that we have at our end. Probably it could be useful for teaching those particular courses. So overall, I think all of us are familiar now with the EV architecture, right? So when we are modeling an EV, we have to place emphasis on each and every component because together it will be something that will be giving us the performance of the electric vehicle. So here we have given a snippet of what the electric vehicle architecture for a pure EV actually looks like. Okay, so we have the battery pack connected with a converter. The converter is actually through the converter we are powering some motors which will actually spin the wheels. So here in the image, it's a the motors are typically shown only for the forward wheel. You can have uh, forward wheel, rear wheel, both sort of places you can actually place motors. And interestingly, one thing that we also are looking at is that it's not just modeling the components themselves, but also trying to see how the whole energy is actually transmitted through each and every component. So not just modeling the component, but also looking at how we can model the thermal and those aspects, which are very important when we want to understand the overall performance of the vehicle. So if we represent it in terms of the different subsystems which are there, so whatever we talked about now is related to this particular subsystem, right? We have motor, power electronics, battery, cooling system, but the vehicle dynamics will be coming specifically from the modeling of the forces acting on the vehicle. That is what we will be looking at today. And overall, the best way we can test it is to actually create a system level model. So not just the vehicle, we have to combine it with a controller. We should have model of a driver, and then either we can go with drive cycles, which means that when you take a particular vehicle on the road, it will have a certain velocity characteristic, so that relates to the drive cycle. Or in many cases, if we are working with particular test scenarios, we can also have those test scenarios integrated. If we are able to build a model at this level of detail, then only we will be able to capture the system level performance of the vehicle. Okay. If we miss out on any of the particular components, then chances are that that will also reflect in the overall performance. So we will not be able to exactly match what the performance of the vehicle is at the overall level. Now, when we work on projects such as this, specifically, a very important outcome in the very end is that we actually come up with a real prototype of the vehicle, right? Something all of us can actually relate with. We want to build a real vehicle prototype, but building a real vehicle prototype in the very beginning could is not actually something that is preferable. Why? Just to give you an idea, I will illustrate some learnings from the industries. So here, I have a user story from one of the very well-known companies, right? We all know and identify from the logo that this is a Tesla. So Tesla is very well known for having very good sort of mileage for their vehicle. So how do they do that? They don't go and directly build a physical prototype. They do some very interesting studies. So what they do is that they actually build MATLAB models for each and every vehicle component, and they try to identify how the entire energy is being used. So for an EV, we can all relate that it will have a certain battery capacity. So we can charge the battery only up to a particular SOC. And the more efficiently we are able to use that energy, the further the range that we can sort of achieve. Okay. So what engineers at Tesla have been doing over the last years is that for each and every component, they have built models and they identify how the entire energy is flowing. So the more the energy we are able to sent to the traction part, the more efficiently it is used, the more the range that we will get. Okay, so this is something that they have done. So they have not directly created a physical prototype, that they do later. Once they understand how the whole energy flows, they identify components where you have inefficiencies and then try to find out how they can build it better. So the process that they follow is something that is common to most of the automotive industries. So the process that they follow is called as model-based design. So long before, in the very early years of MathWorks, what we started to do was that we tried to interact with the automotive industry and try to understand that how they actually design their vehicles. So what we found out was that for the automotive industry, it's very important that they start with some requirements. So they will have some requirements and they will have some prior research also that they have done. Based on that, they start creating these different designs. Okay, so they will create a model of the motor, they will create a model of the transmission, they will create a model of the battery, and all of these, if you see, uh, uh, they sort of do it just by models. So they are not building any physical prototype. Once they have done this thing, they would be building the control logic for all of these components, and then the control logic they will sort of implement on different sort of hardware. So they will not, they will bring in hardware where they will generate control code, and then they will try to see whether the controller is able to control the particular vehicle in the manner in which the requirements have been set. Once they validate everything, only then they finally go and integrate it with a real vehicle and then try to test it out. The reason is that the reason they follow this entire process is that one thing is that the requirements are connected with the model throughout the whole development cycle. Okay, and at each level, so after you design, you are able to test and verify whether you are able to meet requirement. Once you do that, you generate code. You generate code on different hardware. Then again, you verify whether you are meeting requirements or not. Test and verify. So if you have testing and verification at each of these steps, finally, when you integrate it with a vehicle, actual vehicle, there is very less chance of encountering any errors. Whatever design we have specified, we are able to meet that design in the very end. Okay. So this is a overview of what is known as the model-based design. And it's very important that even as faculties, we inculcate this learning in students, that whenever you are working on a project, do not just go and start designing. Understand that what that particular system behavior would be as a requirement. Then when you build that particular first, let's say, component, then try to see when you are you able to meet that requirement or not. So if you follow this stage, you do not have to go to the very end to find out whether your design is working or not. You can do that at each and every step. Okay. What other benefits are there? There are some interesting other benefits which are there when you have something like a system level simulation. This is what industries have been telling us. So as of now, what I have is the V-level model, which many of the industries actually follow. So some of the things is that you are able to understand how a particular system actually behaves. Okay. Then we are also able to evaluate different design alternative. It's not always that one design would be different sizes of capacitors. We can go with different sizes of inductors. So we can evaluate different design alternative. Thirdly, we can actually optimize the entire design. Why? We are doing system level simulation, and whenever we optimize a design, we just don't optimize a component. We are trying to meet certain overall performance. So that actually is very important that we do it at a system level. Okay, so along with this, because we are able to see interaction of between the different subsystems, understanding how energy is being transmitted between them, where all the losses are occurring, we can understand and the different trade-offs that are there when we come to different design choices. And we can also see that is the requirement feasible. So someone might give me a requirement of, let's say, a very high performance, okay, and then at a very limited cost. So then is the requirement actually feasible or not, is something that we will be able to assess even without building that particular vehicle, right? So let me, if you have any questions, please feel free to let me know. I will take one step and ask something and share something that we have seen many of the students, some of the students teams use. So many of the student teams actually also use this sort of a workflow, and they have found some very interesting studies. So one thing is that with a simulation, how far can you go? This is one question that all of us have to sort of think deeply about. How far you can go with a simulation? That's an important question. And then how closely it would match the performance of a real vehicle if you take it on the road. So let me share one user story that will give us some idea about how students are taking it and get some learnings before we start with our learning journey. Let's get some learnings from there. Okay. So I hope the videos actually play finally. So before building machine prototype, we have to answer a lot of questions. Okay. Simulation can definitely answer some, but there are some interesting things that we can also learn from who are the users who are using this in the most advanced way. Okay. So this story is taken from a Italian uh, student body. So they participate in a lot of competitions. Okay. So there they were taking part in a student competition, and the thing that they did was that they started building certain models first, and then they tested that particular model in comparison with a real vehicle. Okay. So pretty big team, 130 members are there, and over a period of time, their rank actually started to improve when they started using these sort of workflows. Okay. So here, if you see, it's a simulation of a EV track. You can see the vehicle moving about in the EV track. It's known as a skid pad maneuver. So the track, if you see, it moves in a certain way, and they build a model of the vehicle. Okay. So if you see here, what they're doing here very quickly is that this is the video of the vehicle exactly on the track when it is moving about. Okay. And at the right side, you can see that they have overlaid that particular model on top of a simulation. And you can see a very good match when it comes to the performance of the vehicle, right? I will just re-emphasize this part. So they have taken this particular vehicle on the track. They have used a simulation. They have seen how the vehicle performs on the track using the simulation. Then they took the real vehicle on the track and superimposed both the results. So this is simulation, and this is the real vehicle that they have built. They superimpose both of them together, and you can sort of visualize that how closely they sort of correlate to the performance that you see from the simulation. Yeah. So exactly the maneuver that we saw, it is executing that exact maneuver here. Okay. So now my question is to you is that what difference do you observe? Is it totally same, or is there any difference here? So I will just make a brief pause here. Similarities we can definitely see, but what differences do you think are there? Anyone? I'll just quickly take a look if there is anything in the chat. No difference. Okay, so that's a good feedback that there is definitely no difference. It totally matches. So we are very happy. So simulation and experimental results are matching. Nothing like that in to convince people, right? Both of them are matching quite well. Anything else that you observe? You have to observe very carefully, actually. Okay. So here I will clarify. So here, if you look at the maneuver, there is not much room for the driver to do much, I would say. Okay. because it's a very, I would say, uh, very specific maneuver that they're doing. Okay, so although different drivers can actually drive in different ways, but there is not, in that way, it's not, I would say, much of a difference. Okay, so I will add here, if you look very closely, do you see a vibration? Just look at real vehicle and simulated vehicle. So in the normal vehicle, see, there is vibration which is there, right? It could be due to the road, it could be also due to a sort of the suspension. So there is a vibration which is there, and the students were able to measure it with sensor and quantify how much vibration was there in the vehicle. Okay, so there was a vertical vibration which was there, which the simulation model was not capturing. Okay, so for the students, it's a very interesting sort of a learning that, okay, I have modeled only the longitudinal vehicle dynamics. I have not sort of modeled uh, uh, the lateral dynamics in detail. So that's why I see this sort of a difference. Also, if you look at the road, a road has a certain tire, the road and the tire has a certain interaction. That interaction is very critical when it comes to the performance of the vehicle. That is also one of the area. Yeah. So one of the things is that road and tire model, how you can do, that is very critical. That if you combine with vibrations here. So the physics that you are able to capture in a simulation actually determines how accurate the results will be. But for many use cases, like in this case for them, the timing, okay, so the timing they need to reach a certain set point, that was more important. So maybe it is because of the video. I'll just pass one particular screen, or maybe should I stop the video? I hear that there is a screen lag which is there. Okay, maybe I will just see if I can stop my video. And so just to conserve bandwidth, I have just stopped the video. Are you able to hear me fine now? Uh,
Yes,
is
sir.
it even
Actually,
okay? Okay.
you're audible now. In between, just your voice was
Okay.
breaking, so I think they were unable to
Yeah.
hear. So you can repeat if possible.
Okay. Okay. So the point here is that the physics that you are able to capture actually determines how accurate your results will be. So specifically for the students, the challenge that they faced was that they were not able to capture the interaction between the tire and the road accurately. So their models there were not very sophisticated. The second thing challenge that they had was that uh, uh, specifically they saw that uh, uh, the specific parameters that they actually use for the tires was also not something that they could directly find. So those were things that where they've actually faced a lot of challenge. Okay. The other thing that they found advantageous in comparison was that these students were actually introduced to multi-domain engineering systems, and they found that when they actually look at any sort of system in a multi-domain way, it was very easy for them to collaborate together. So that was one advantage that they saw when they came to modeling these sort of systems. Okay. So they identified that because they have big teams, so they have almost 130 members, it's very important that they should learn how to actually work with multi-domain models. Okay. So this is one more thing that we can sort of emphasize from their learnings. Okay. So one way we sort of address it is to introduce students, faculties, or users in the area of multi-domain modeling using the Simulink and Simscape platform. So this is one way where we can take any sort of a vehicle model. Maybe there are different sort of domains which are already there, and they can be combined together, and the performance of the system we can determine. So you can already gauge what sort of components the students use for their application. So specifically, they use multi-body. This is something that is quite advanced. but they also use models from the Simscape library, which actually help them build such a model. Okay, so let's take one step and try to come up with a vehicle model, an EV vehicle model, looking at what these sort of students were using, and try to understand how they build that particular model. Okay, so the model that I'm using today is a simple electric vehicle with the longitudinal dynamics. Okay, so you can find this model at the link I have mentioned here. Okay, so I have to see if it will work with the older versions of MATLAB. But if you have MATLAB online also, this particular example should work fine for you. So the only library that I'm going to use here is the physical modeling library, which is Simscape. If you have Simscape at your end, the model will work fine for you. Okay. So this model is something that you can directly access right now if you have access to MATLAB and Simulink, and if you want, you can open it at your end also. So what I will do is that I will open that up using MATLAB that I have at my end. Okay. Okay, so this is the MATLAB window that I have. I have already opened up that particular vehicle model in the Simscape environment. I will show you how this vehicle model has been built. So basically here we have simplified a few things so that everyone can actually sort of get a feel about how this is actually done. So the library browser, if we go here, okay, so it's just opening up library browser at my end. So here in the library, in the very left side, if we go and have a check, there is this library known as Simscape. This has everything that I need to build my electric vehicle model. Okay, so if I look here, I can actually model the driveline. So I can model specifically the vehicle body, different sort of gears, different sort of engines and motors, just to give you a view. Different sort of motors and engines are all there, and all of this is multi-domain. So I can model different sort of components interacting together here: clutch, brake, different sort of brakes, rotational, translational. So all of these components I can model here, and I can combine them together to model the entire vehicle. Okay. So one critical thing that I'll use here is the model of a longitudinal vehicle. So here you can see the vehicle body. This is what I can use to actually model a particular vehicle body. Okay. I can give the braking force, I can give the axle, vehicle speed, wind velocity, and this would model the longitudinal characteristics of the vehicle. Similarly, I can model the tires, I can model the different sort of transmissions which are there, and I can connect different sensors here to understand how the vehicle is moving about. Okay, I have rotational power sensor, translational power sensor, different sort of gears. So this library, as in what it has, will allow me to model an entire vehicle, and also not just the vehicle, but also the, if you look here, I have the battery. So I can model an entire battery pack. And then I have components here. So in the foundation library, I can model the thermal aspect of it also. Okay, there are thermal elements, resistors, conductive heat transfer. All of these components I can combine together to have a full full EV model with all the different multi-domain components connected together. So let me take you through the model. Right now, I'm not building it from scratch. It will take a bit of time. So let me just take you through the model right now. So this is where I have the vehicle body. Okay, so if I just go inside, I have the brake subsystem and the chassis subsystem. Okay, so both of them I have sort of kept here, and both of them are combined using this shaft that we see here. Okay, this shaft connects both of them. Also, there is an option to sort of model the incline. We can look at the vehicle body to understand how this actually works. So here, if you see, this is where I'm modeling the vehicle body. Okay. Uh, we can model what is the amount of wind which is there. And then this vehicle body actually models the forces on the vehicle. Okay, so if I look at the description, it represents a two-axial body in longitudinal motion. So it will account for body mass, the aerodynamic drag, road incline, and weight distribution between the axles due to acceleration and road profile. Okay. So in settings, I can see all the different parameters which allow me to model this particular vehicle. I can set the mass here in kg, number of wheels per axle, 1. So it will have 2 axles, we can have 2 here, and the distance of the different axles from the center of gravity. Okay. This is the main part. Drag part I'm modeling here, where I model the vehicle frontal area. So around 1.33 meter square is the area. I have a drag coefficient set here about 1.2. Air density I have taken. And I think pitch and all we have sort of not used here, but if needed, we can have pitch dynamics also. So for the vehicle, if you look, we are not modeling the normal forces here as of now, but if we want, we can do that also. There is a hub which is there. Each port represents the hub. With the hub, we have connected 4 tires. So there are couple of rear tire, rear left, rear right, and then I have frontal left and frontal right. Okay, so this is related to the vehicle body. So if we go one level up, this is where we have the braking subsystem. So right now, what we have created very simply is just a vehicle body with the tire, and then we have 4 brakes for the 4 tires. So these are as of now specifically disc brakes, if I remember correctly. Yeah, and we have given the disc brake parameters here. Okay, how many brake pads are there? What is the mean pad radius? How are we giving input to the brakes? So all the brakes we have taken, combined them together through the SimScape bus, and we are applying certain forces on the particular brakes. Okay, so these brakes actually have to be, so if you see this P port, this applies a certain force on the brake. So if you go one step up, we see that we are applying a rear brake pressure and front brake pressure. There is a vehicle incline, and then we are trying to see how the vehicle is actually moving about. So this vehicle as of now doesn't have an engine. So it still doesn't have an engine. We have the vehicle body. We are just putting the vehicle on an incline. So there is a certain slope which is there. What will happen if the vehicle has a slope? It will start coming down with a certain velocity. And then we are applying a certain tire pressure. So these are like, if you see, this is a step function. At a certain step, around 12 seconds, a certain brake pressure will be applied and the vehicle should come to a stop. Okay, so very simple model for us to get introduced to how to model vehicles. So I'm just running this as of now. And in result, we can clarify that whatever equations we have actually worked with, do they actually describe the performance of the vehicle like what we sort of get from the equations. Okay. So right now it had run the simulation, and the result, it is sort of, it has opened on a window at my side. So, okay, so that's a very good question. I will come to the question just in a bit. Just give me one moment. Yeah. So now here I can see the results together. So what I see here is initially the vehicle velocity keeps rising, right? Just let me see. Yeah, speed keeps rising. We have written in both miles and then speed in kilometer per hour. And then if you go at 12 seconds, if you see, we have started applying the brakes. So it reaches a certain velocity, it becomes stable. And then as we start applying the brake, the vehicle sort of starts deaccelerating and then it comes down to 0, right? So this is what we expect from a vehicle which doesn't have any engine. Okay. So There is a question here that can MATLAB modeling be used for only four-wheeler or can it be used for two-wheeler and drones for well? So this is a very interesting and common question that we get, that how can we extend it for any number of wheels? So then what we have to use is that you actually have to either sort of go with a vehicle body and you have to modify it only for one sort of axle and two wheels, or there is also one way in which you can actually model it very easily for two-wheeler. I will show it in a bit. There is a very interesting shortcut that you can use to actually model two-wheelers. Okay, I will show you the example just in a bit. So as of now, we have not taken the road profile. We have assumed that the road has a certain incline. So we have given it a constant incline. But if you have a road profile, then you can use a block to import a road profile also. How can you do that? So what you can do is that we can use signal generator or signal editor. So there is a nice block which is there called signal editor. So here we have given it a constant value. If you have data, let's say if you take data from any road incline which goes up and down, then you can go here, use the signal generator, use the data, import from that particular road profile, and then you can bring it here and connect it to this particular subsystem. Okay. Interestingly, if you do not have any such profile and if you want to just test what happens if you use certain, let's say, road curvatures, then you can edit and create this scenario. So the signal editor opens up with an interface, looks something like this, where you can actually create different signals. Okay. So you can create different road profiles just like this. You can actually draw them also. Okay. You can draw different road profiles and then you'll sort of generate a profile here and then you can import that data. That should also work. Okay. So all in all, depending upon what sort of roads you are working with, you can actually generate different sort of curves and then you will have that profile also at your end. It will generate points for you, which you can then use in the simulation. Okay. So very easy for you to actually look at how you can do the road profile. So now I will come to the part that now our car doesn't have an engine. So what should we do? So then we can actually go and take the vehicle model and combine it with a engine model. So how can we do that? Again, the Simscape library browser can help us. I will just show you what I have built at my end. And the same thing can be replicated when it comes to this sort of models. Let me quickly open up another model just to show you how you can include that part also. Okay. So by the way, I will just share. So if you download the example that I talked about, which is the one that I just shared from the GitHub page, so it will have folders like this. The one example that I just showed is part of the longitudinal motion. Okay. Second example talks more about the electric powertrain, how you sort of combine it with an electric powertrain. So I will just open up that model now. Did I click it properly? Okay, so yeah, it has opened up here. So till now, what we have built is just the vehicle model here, right? In the last example, this is what we built. So here we are applying a braking pressure, but to ensure that the brake moves, what we have to do is that if you look here inside the vehicle body, we have made two different changes. This is what we built before, only the vehicle dynamics, and we had brake pressure connected to that. But now what we have is that we have our drive shaft which is there. So here we have taken the two different tires. Okay. And if you look, we have a subsystem here where there is a torque sensor and we have connected a differential here. Okay. So we have taken a differential with the drive shaft teeth ratio and crown gear defined here. And using this differential, we are combining it to the drive shaft. Okay, so this drive shaft is then connected to the electric powertrain where I have the electric motor here. Okay. So here I have not gone into detailed and model an entire electric motor. Here what you see here is a motor and drive at the system level. Okay. So this is a motor and drive at a system level. And then if you look here, what we have is that this is powered by a battery. I have a battery block here from the Simscape library. And I'm measuring the SOC of the battery also, right? This is something we are very interested in, that what is the state of the battery when it moves to moves through a certain path. Connecting the battery with the motor, we cannot do it directly. We need converter. So we have a DC-DC converter. Why? Because battery, if you see, it has a certain voltage. Okay. And the motor, if you see, it will have a certain output. So we have parameterized it by the maximum torque and power. Okay. So this DC-DC converter ensures that exactly that we are able to sort of meet the requirements of the motor. Motor will have a certain DC requirement. That voltage requirement we are actually meeting by using this DC-DC converter. The output, so the motor here, if you see, this is a nice example of a multi-domain system, right? It has electric components that you see in blue, which is related to the circuitry and the magnets which are there. The green part refers to the mechanical component. So there is energy being transferred from the electric circuit to ensure the rotation of the motor, to spin the motor. So that angular conservation principle is applied here. And what I have here, if you look at the orange component, this is related to the thermal part of it. So if you see here, I can see this option that says show thermal port. This actually models the thermal component of the electric motor. So by definition, if you see, it is a multi-domain component, but thermal I have not gone into a lot of detail. I am just insulating that particular motor here. If I want, I can also model the different mechanisms by which this motor will transfer heat to the surrounding. So if I say, let's say, want to model a conductive element, then I have to have conductive block, conductive heat transfer. If I want to model radiation, then I have to have radiative heat transfer. And all of them have to be combined together if I want to model that sort of a thing. So if I want to model other sort of characteristics, then instead of insulated, I would have to sort of connect them to this particular model. Right? So multiple sort of modes, and then I reject this heat to the atmosphere. So then I can have a temperature source. So this is how I can actually model any sort of thermal component. So just to simplify things, we have made it insulated so that we can actually see the motor temperature rise. Okay. But you can actually model different sort of thermal behavior also following this sort of an approach. Okay. So here, what are the things we are modeling? We are modeling the motor and we are trying to see what sort of torque it is generating. So we have a motor reducer here, and then it is connected to the gear. Electric part we have modeled, and the thermal part also we have modeled. So now we have an electric vehicle which is connected to the vehicle body. Okay. And then we can simulate. We have given it a certain drive cycle. So controller part, I'm not going into more detail. Controller is a very basic controller we have used. What I believe it is just some PI blocks. Okay. There is a certain motor speed reference. We are just converting it to torque. And then, so basically we have a drive cycle source. Drive cycle source means vehicle velocity changing with respect to time. Whenever it is accelerating, I will take it as that the wheels are going to spin faster. So I will converting the motor speed into a torque command and trying to meet that. Whenever it is deaccelerating, I have brake pressure, which I also try to use the controller to meet. Okay. So this is how it actually works. If you run it, it is like running a full sort of a electric vehicle simulation with longitudinal dynamics, and then we can see how the results are. Okay, so now it is running, and this is the part where we can go and visualize. So velocity we can compare whether it is able to meet the velocity that we have designed it for. So here I can see that result here. Okay. So vehicle speed and wheel speed, we are able to meet according to our requirement. You can see that both of the curve, reference and the vehicle speed are sort of overlapping here. Similarly, torque also we can sort of compare how the vehicle is able to meet the different torques which are there. And we get a curve like this here. Okay, so torque on the rear lift, brake, drive torque, all of those parameters we can see closely. Okay. So this is a very simple example of how we can do a full-scale electric vehicle model uh, with the full multi-domain capabilities which are there, and then visualize the result at the same place. Okay. What next from here? So what would be the next step once we do something like this? Is to look at the, so you have to make a guess. What would be the next step? What have we missed here? I showed you some visualization. What did we miss? Okay. So to give you the answer, the thing that we missed now, vibration definitely, we did not model the, uh, we did not model that aspect closely. So the thing that we actually missed was that, that's also true, motion, but we are able to measure using the sensor. We are able to see some sort of results that how it is able to meet that. What we are missing as of now is the motor thermal characteristics or the thermal characteristics of the vehicle. Okay. So here, for those of us who are actually very much interested in understanding that what is the temperature which the motor reaches, so then we can actually look into the motor cooling aspects. Okay, so this is not something I would get into more detail, but I will just, for a closer scenario, I can show you that people actually model the motor in more detail, and then they try to see that how you can model the motor cooling system, right? So I was talking about this before. So you can model the different conduction, convective, radiative capabilities of the motor. And in many cases, what we will see is that the motor temperature also rises when we have a vehicle which is running and then you don't have enough coolant. So here we have a model of a tank which has a certain coolant fluid. There is a pump which will pump this fluid through a certain pipes, and then it runs through the motor. The pipe runs to the motor, takes the heat from the motor, rejects that heat to the surroundings. So we have a heat exchanger here. Okay. And then we try to see what is the temperature of the motor. So these are studies which give us very good idea about how to uh, sort of optimize the vehicle performance coming from the thermal side. So if you do this sort of study, we would be able to also visualize the temperature of the motor. So very quickly, let's go through this one. So here we are basically seeing, in addition to whatever we have seen, what is the SOC. So we are trying to cool the motor, right? Where will the energy come from? Yes. So when we're trying to cool the motor, the energy will also come from the state of charge from the battery itself, right? So the state of charge of the battery will also drop when you are trying to do cooling of the motor. So here we have a plot of the state of charge of the battery, which is falling with respect to time. And then we can look at the motor temperature. We expect that the motor temperature here, if you see, initially it is showing somewhere near room temperature, but then it rises, goes very close to 100. But because we have a coolant system which switches on when the temperature goes to 100, the motor temperature comes down, right? Again, it goes near 100, we have the coolant switch on, the motor temperature comes down. So we can create different sort of algorithms to optimize that, okay, my motor has, let's say, a threshold rating of temperature given as 100 degree. So I have to build controllers to ensure that the motor temperature does not reach 100 degrees. Or somebody can give me a temperature range in which my motor operates efficiently. Then I have to optimize, or then I have to design controllers to ensure that the motor operates in that particular region. So these are the things that then I can focus on. Okay. Do let me know if there are any questions with respect to this one. And this does not mean that I'm just going to focus on motor also. What am I missing? One important characteristic here is that for an electric vehicle, if you look at the electric powertrain, motor I have modeled. So as of now, to model this, I have used MATLAB version 2024B. So there is where I am opening it, but it should open up with earlier versions also. If you have Simscape, then this model will open up at your end. So right now I have thermal model for the motor and drive, right? I can have thermal model for the converter also. Exactly. BMS also can be modeled. Okay. So just if I go to Simscape, uh, I can actually go to this particular blocks also. This doesn't have a thermal port. I can show thermal port. So I can model thermal components of mechanical of the electric converters. I can model thermal of the battery also. So I can have a thermal port for the battery. And the more accurately I'm able to model that particular system, the more accurately I will be able to measure that what will be the SOC of this particular EV when it goes through a particular maneuver or a drive cycle. So to model battery aspects, to model the BMS, the library that you need is also part of Simscape. I'll just point you very quickly to that part. So just go to Simscape. There is a dedicated library related to battery now. You can model them starting from single cells. So we have multiple of these libraries for modeling cells. You can have a battery model, a table-based battery model. We have very detailed model of batteries also. And then for BMS, we have components that will allow you to estimate. We can estimate the capacity, filtering. There are multiple of these SOC estimators: adaptive Kalman filter, adaptive Kalman filter variable capacity, Coulomb counting. Okay. So whichever method I'm using, I can use these blocks actually to do these things. You don't always have to create the entire algorithm, although it's a good thing that you can create your own algorithm and try to benchmark it to these particular blocks. So you can use these libraries to actually do that. Apart from that, for a bigger, let's say, battery, you can do cell balancing. So we have modules for cell balancing. For current management, so battery, we can implement CCCV charging, discharging things. And we can have protection also. Okay, so different sort of protections we can also sort of ensure that we can actually use. So, so any component can be modeled. So that's a good point. I'm not sure which component you are specifically looking at. So whichever component you are trying to model, you can actually model it here. Okay. So voice, I think some of you are having a challenge with the voice. I'm not sure why that is. I am actually having the mic pretty close to me.
So you're audible properly. It may be due to
Okay.
internet issue at the
Okay. That could be one thing. Yeah, that could be one thing. Thank you for the feedback. So no matter which module you are particularly working with, you can directly come here and sort of identify that particular block. And it takes a bit of time. Uh, if you just spend a bit of time going through the examples that we have already, which are there, you will get a very good idea how to do that. So let's say if you are working with battery, okay, if you want to know more, so then you can actually go and sort of look at the help document. You will get a lot of examples which are there, which will give you some idea about how to use that particular block. Okay. So now I will show you some advanced advanced things compared to this one. Okay, so this is something which we have, which will allow you to model a multi-domain system. So right now, whatever we have done, it is still a longitudinal model that we have used, right? So now the thing is that how to now take this and go for, let's say, uh, 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 how to now take something like this and then go one step above. Okay. So I'll just close this. I will just share a couple of slides and then we will look at some more examples. So I will share the resources for you. I think most of the things are already there. So specifically, one thing that we can do is that right now, whatever we were doing is related to longitudinal modeling. Okay. We can also model the vehicle body at different fidelities. We can model 3 degrees of freedom. We can have 6 degrees of freedom. So there are two ways we can go about it. Either we can write the equations at our end and do that. But specifically for MATLAB, we have libraries that also help us do something like this. Okay. So there is a whole library of different sort of approaches for modeling the vehicle body and sensors. We can look at that to go ahead. So right now we work with this. This was the longitudinal dynamics. Okay, this is the simplest way we can go about it. We have also blocks that allow you to model the entire vehicle body and sensors at different fidelities. So here it is very easy for us to go with four-wheelers, or we can go with two-wheelers where we have motorcycle, or for commercial we have uh, existing blocks that model equations for vehicle body with 3 axles, trailer bodies, vehicle body with 3 axle, 6 degree of freedom. So multiple of these blocks are already there. We can directly take them and model the vehicle body. Okay. So we can take the learnings that we have and combine them together. So what we have, we can take the either a simple vehicle body. We can take 3 degrees of freedom of the body model. We can combine it with steering, with a system model, with a transmission. So here we have combined multiple things together, and we can combine 3D scenarios also. So MATLAB very closely connects with an Unreal Engine. So we have support for Unreal Engine, where if you combine these things together, you should be able to do what you have here. We can have different sort of scenarios that we can test in a 3D environment. Okay. So the maneuver that we see here is a double lane change maneuver. These are the scenarios which we can actually implement if we go by this way. Okay. So there is a double lane and those things. So those things is something that we can try. Okay. So this is based upon a different set of library, by the way. So the library that I'm talking about now is known as the uh, vehicle dynamics library. Okay. So where can I find it? So if I'm trying to install anything separately, there is an add-on manager here, get add-on. So all of these libraries separately, if you want to sort of explore, you can find in the add-on explorer. Okay. So meanwhile, as it opens, I will just let it open, and I will just open the model also at my end so that we can quickly have a check with that. Uh, okay. I will just show something here and then I will show you the libraries also. Okay, let me just check if the library has opened. Okay. So add-on explorer is the place where you go and search for the libraries. So it is available in the older versions of MATLAB also. I am using this add-on library from somewhere like 2019. It should be there. So previously we checked with Simscape. Okay, so this was the Simscape one that we just saw. Simscape electrical battery, Simscape multibody. We'll come to multibody a bit later. Simscape driveline. What I'm using now is known as the vehicle dynamics library. So vehicle dynamics block set. And a number of industries actually also use this block set, right? It's a very interesting block set where it provides pre-assembled automotive vehicle dynamic reference applications for cars, trucks, and two-wheelers. Okay. So it includes components for propulsion, steering, suspension, vehicle body, brakes, tires, and driver models with the controllers also. And we can interface it with an Unreal Engine to visualize the simulation and communicate scenarios information. Okay. It also integrates well with something known as the virtual vehicle composer. This is something that I will show you in a bit. Okay. You don't have to build everything from scratch by connecting things together also. Okay. And the best part of all of is this, that whatever you can design here, you can generate code out of it and do integration testing. You can do software testing. You can do hardware in loop testing. Industries use this a lot. Okay. So I will just take one example of the vehicle steering that we have here. Okay. So it says it is already loaded. Okay, good for me. Yeah, it is already loaded at my end. So now I have whatever I've shown before for the simple scenario, I have built something very similar, but now the fidelity has changed. So now I don't have a just a longitudinal dynamics. I have a 3 degree of freedom vehicle body that I'm using here. Okay, and then I have a vehicle track also, a dual track. I have defined the different forces. External longitudinal velocity is what I'm giving. I can define different external forces here. Vehicle parameters I can give longitudinal. I can give the lateral also. Okay, so I can parameterize it both from longitudinal lateral point. Aerodynamic and all we have already seen before. This is something that we can do. And here, just for a simple scenario, we have connected a steering to this one, kinematic steering. We are providing a steering angle and we are just trying to see how the vehicle is actually moving. Okay. So if I just run this, so it is running the model, it is compiling everything. And then in visualization, I can actually see, okay, it has open visualization on my side. Okay. I'll just quickly run it again. We can see how the vehicle is actually moving over a particular track. Okay, so it is animating at my end only. So it is showing the entire animation and the track also it is showing how it is actually moving about. I don't know how to actually ensure that it runs at your end. Okay, I know one way. Okay, let me make it 100 seconds, then I think it should work. So here you can see it is just moving about in a circle. So we are able to actually, if we connect this with the 3D Unreal Engine, we should be able to see that particular behavior in a 3D environment also. So that is also something that is possible with an approach like this. So coming to the second part, so this is again like a higher fidelity which I can model, and this is something that industries do a lot also, still at a system level, and we can see the performance of the vehicle. We can see, so here we have just put kinematic steering, but here we can also have different sort of steering. We can have different sort of parameters here. So those we can do. We can go one step further also from here. What we can also do is that so this is some, we can also import CAD models. So let's say I have a physical geometry of a particular component of the vehicle at my side. Let's say if I built it using tools like SolidWorks, I can convert them to an SLRT file. I can export them. Then I can open it up in MATLAB and I should be able to see all the components that I have and how they are connected together. So Simscape Multibody will allow me to work with different assembly models in CAD, add physical tire steering rod, test bench modules, and then I can run them and I can visualize how the vehicle is actually going to move on the road. Okay, so this is a possibility, and this is also something that we see interest both from students as well as industries also nowadays. Okay. So there are some examples that you can actually explore a bit more. Uh, Probably I can link them with you later. Okay, so let me. So there is a question that are there any libraries available for drones modeling? So that's a good point. We have a UAV library. So just like the add-ons that we just saw, not to go far from the agenda here, but I will just quickly show you that there is now a UAV library which you can try to sort of uh, access from the add-on explorer, and using that you can model UAVs also, and you can also visualize them in a 3D environment and see how those UAVs actually behave. So I will just quickly show you that and then I will go ahead. And this is a pretty good also in terms of teaching, I would say. So we have a UAV toolbox. Using that, you can actually model UAVs very easily. Okay. I've not installed it, but you have UAV toolbox. And if you're using specific PX4 autopilot or different drones, then we have also something that will allow you to control them. Okay, so that is also there. Now I will show you one very interesting thing that we have. You always need not build something from start to end. There is a virtual vehicle composer app from which you can very quickly build this sort of models. Okay, how do we access the app? So at the very top of MATLAB, there is a place called apps. This is where we can go and access this particular thing. So in 2024B, if I I have apps here at the very top. Just search for the virtual vehicle composer app. So the good part about this app is that let's say I am a person who wants to do system level simulations in a very I am on a very short time and I want to create an entire system model of a vehicle. This is where I can go. I can start with a new model here. It will enter a setup screen where it will ask me, what sort of vehicles do I have? I can go with four-wheeler, I can go with two-wheeler. Accordingly, it will configure the components that it will use. Okay. So let me just go with four-wheelers as of now. Conventionally, architecture I can also choose. So here, if you see, I can go with one electric motor. So there would be either a front wheel drive or a rear wheel drive. I can go with two EM, means I can have uh, uh, two sort of motors here. Then I can have dual front, dual rear. Okay, so different architectures I can actually select. So let me go with the simplest one, electric vehicle, let's say two electric motor, something like this. It is showing me how the architecture is. Okay, so I have two wheels, I have a battery, I have one motor connected to the differential, which is spinning the front wheels, one motor spinning the rear wheels. Okay. Now I can choose which set of libraries it will use. Just give me one moment. Okay. So I can choose here what sort of libraries I have. Should I only go with longitudinal? Should I go with combined longitudinal and lateral? Okay. So, okay, just give me one moment. I'll just take a call quickly. Okay, so I understand we are nearing perhaps the dinner time, so I will not take a lot of time from your side. So I will just quickly give you the way this works. You can actually identify what you are looking for. You can choose which set of libraries it will use. And then if you just go to the next stage, it will take the configuration you have chosen, and then it will take you to a screen where all you need to do is parameterize everything, and very quickly it will parameterize and then generate the model for you at the back end. Okay. So here you see it has taken whatever inputs I have given, and then it will sort of build the model. I'll just show you an animation of how this works so that all of us can save some time. Okay, so again, just to quickly show virtual vehicle app, it will open up something like this. We can create a new thing. Select the type of model we are working with, a vehicle. Select the sort of powertrain architecture. Select the different dynamics. Library, we can go with Simulink or Simscape, and then if we just say go ahead, it will create the entire vehicle model for us. We have to parameterize and identify the values. So for each of our vehicle, we will have different parameters. So ideally, you can think of this like it is taking the entire equations, connecting them together, and then we are giving it the values of those particular parameters. Once we have done that, it will create the entire model for me end to end, and then I can actually very quickly go and change components also and visualize them also. Once we have done everything, we can actually create scenarios to do testing. We can have just steering scenarios like what we saw. We can have 3D scenes also. And we can create this sort of tests to test that particular vehicle in different scenarios. So as of now, for this, you cannot create 3D solid 3D geometries. That we have to do on our own. This will create everything from equations right now. So it will create something like this with all the components connected together. Okay. Not by, this is not, this as of now doesn't support the 3D solid one, that separately we support. But even here, whatever we are creating, we can use 3D environment and we can test that particular vehicle model, because in the end it's equations only, and it will have a certain behavior that we can visualize here, right? So just to show once again, so those things we can show here. So even though we have not created a 3D solid assembly, it will take the Unreal Engine, take the vehicle models which are already there, and that we can visualize. And then we can go back and customize it as we need. And similar thing, if we have our own 3D solid geometry, that we can actually bring in SolidWorks and go ahead from there. It won't change much, but this part as of now is not supported by the virtual vehicle composer. Okay. So with this, I will stop here. In many cases, what we can also do is that we also have some vehicle templates. So in Simscape, let's say if you're working with, let's say, not just a two-wheeler body, you are working with trucks, you are working with, let's say, a bus. So then from Simscape vehicle template, you can go and also select that sort of vehicle you are working with, and then you can look for the maneuver in different sort of environments. What this helps you is that it helps you to go from a requirement to a system level simulation within minutes. So we save a lot of time, right? And then if needed, we can, all of this is freely available to you. So it is not a black box. You can go inside, change component, bring in equations, create your own specialized components and carry out testing. So you save a lot of time here. Okay. So with this, I will sort of pause here. So at MathWorks, we are in a place where we interact very closely with industry, researchers, and education. And definitely, all of us have different things to look at. But we actually are very happy to support different sort of initiatives in this particular area, right? We also have now an EV curriculum. So where you can actually model an EV end to end. So if this is something of interest, please feel free to write to me. I'll be happy to sort of share with you what we have, and then depending upon the use cases that you have, you may select particular components that you can use for your courses. Okay. So with this, I will sort of end here. Do let me know if there are any questions. We can take that. I'll just pause on the first slide. If you are in a hurry, you can just note my email and also reach out to me. That should also do.
If anyone has any doubt, you can ask. You can unmute and ask your doubt.
Thank you for the comments, and any question is also a good question. That's what we say at MathWorks. So please feel free to let me know. Okay.
Hello. Hello,
Yes,
Dev
sir.
sir.
Yes,
Yes,
sir.
Hello, sir.
Sir, very
S-
informative presentation by you, sir. Thank you very much, sir.
Thank you very much for your comments, sir. Thank you.
क्योंकि ऐसा presentation हमको अभी तक के मैथ वर्क में किसी ने नहीं दिया.
अरे तो फिर तो
Thank
ये
you
तो
very much, sir.
yes, you. If there is anything particular you're looking for, sir, please feel free to connect to me. Okay.
Yes, sir.
So
Yes,
I
sir.
actually am
Definitely, sir.
part of the education electrification team. So anything related to electrification, it could be electric vehicle, renewable energy, microgrid. I'd be happy to support
Yes.
you with resources, sir.
Okay, sir. Definitely, sir. Thank you very much, sir.
Thank you very much, sir.
Sir, I have one question.
Yes, sir. Yes, sir.
Do you provide the support for simulation of power electronics circuits,
Yes.
some training kind of things?
So we have for academia we have good content. So typically we if it is power electronics, for which application, sir? If you could mention, that would be very helpful.
Yeah, electric
Is it
vehicles,
general?
solar
Okay,
energy.
EV. Okay. So EV would be a bit different because the requirements for the EV are typically different. We typically show how we can model different sort of converters, uh, 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 specifically for, let's say, connected to the battery pack, connected to the motor, or for charging, discharging. And renewable energy, it will be very different. You will be having specifically the inverter we have to design for solar, the inverters we have to design for, let's say, wind systems. So those applications would be very different. So depending upon what is the use case, we can actually sort of plan an agenda, and then we typically do that also.
Okay.
We sort of carry out. So just please feel free to drop me an email.
Yeah, sure.
Yeah.
Thank you.
Yes, sir.
Hello.
Yes, sir.
Myself,
Dr.
Dr.
Dipesh.
Dipesh
Yeah.
Pardesi from Sanjeevani College of Engineering, Kopargaon, sir,
Oh,
Maharashtra.
nice. Nice, sir.
Already I have purchased the campus license for the MATLAB, and I'm working in the field of the MATLAB.
Oh,
But
nice.
the presentation today I have seen, it is really a wonderful presentation. And
Thank you,
such
sir.
kind of support still I am not getting from the math work.
Okay, I will. Perhaps you are in connect with our Pune office, right? I will let them know to reach out to you, and then
Because your presentation
plan
is a
something.
really excellent presentation, and where we really got the feedback how to go in depth.
Yeah.
So if any issue is there, I will drop you the mail also. So please
Sure,
kindly
sure.
support us.
Yeah. Definitely, sir. Would be happy to support you, sir. Yeah.
Yes, because whatever support I have received from the math work now, it is only on the upper side. But whatever you have shown the presentation, it is the in-depth presentation you have shown, sir.
Okay.
And if such a kind of in-depth presentation is shown, then we are ready to run, because we are autonomous colleges, so we are ready
Yes,
to run
yes.
honor courses in MATLAB also for EV or other
Okay.
capsule courses.
Okay. Sir, feel free to drop me an email. I will reach out
Yeah,
to you
I will
directly.
definitely. I have already copied your email. So I will drop you the email, no issue. Actually, Mr. Ankit Kumar is dealing with me regarding the MATLAB, and Mr. Romeo Lahari.
Okay, yeah, I know him. He's from a partner
So
team. Yeah.
he can directly talk with Romeo also, Romeo sir.
Okay, sir. I will connect internally also and let them know.
Okay, I will drop you the mail also.
Okay.
Thank you, sir, for
Thank you,
the
Dr.
nice
Tejas.
and wonderful presentation.
Thank you, sir. Happy to hear, sir.
Hello, sir.
Yeah, please go ahead.
Yeah.
So, Dr.
Yes, sir.
Please, working as assistant professor in CPET Jaipur, we have also a basic license for our college. That the student can use this app or what we call the toolbox in the online
So
MyTech.
there is a way, sir, you can check for that. Okay. So if you're, let's say if you're not unsure that which toolbox you have and which you do not have, then one thing you can do is that type this command VER. If you do enter, it will tell you all the toolboxes that you have. Okay. So specifically for the use cases that we saw today, we were using Simscape along with the related libraries which are there: battery, driveline, electric fluids, multibody. And we also saw powertrain block set. So if you have these libraries, everything that I showed today should work at your end, sir. So if I missed your college, sir, please could you just repeat?
Sir, Central Institute of Petrochemical,
Okay.
CPET.
Okay, CPET. Okay, I know CPET, sir. Yeah, thank you.
Jaipur.
Okay, CPET Jaipur. Okay, sir.
Good evening, sir.
Yeah, good evening, sir.
Sir, you have shown the simulations of MATLAB in some vehicles only. Is there any different types of vehicles we can design in that one?
So different types of vehicles means not just passenger, like load carrying ones and all, right?
Only few things you had shown that simulations, sir.
Okay. So what sort of vehicle are you planning to design, sir?
You have shown the four-wheelers vehicles only in that simulation, sir.
Yeah.
It is only enough for four-wheelers only, or either any other heavy loaded vehicles can be also we can design in that one.
Yeah, I did not show the entirety of it, but we have templates for which you can model any vehicle. If you see, we have something known as Simscape vehicle template, where you can not just model any two-wheeler, you can actually model bus. You can model, let's say, trucks and all. So you can model not just one, you can actually model different sort of vehicles also. So I will just post the link for you. So there are templates using which you can model different vehicles. So we have examples for that. If you want to build it from scratch, that should also be possible. If you want to model each component individually, that should be possible. But we have this thing, which is something created by the MathWorks team only. It has different sort of vehicles that you can model and model in detail. Okay.
Okay, thank you, sir.
So here you can model trucks, trailers, all of those things you can model.
Yes, thank you, sir.
So I hope all the doubts are clear.
Okay, so I think given we are at .9, I will not stop you from going for the for whatever you have planned for now. So let me do one thing. Whatever resources I've shared, maybe I can collate everything and share with the organizers along with the PPT. Please feel free to reach out to me if you have anything, any doubt, or if you are interested in curriculum related stuff also, please let me know. I'd be happy to sort of connect with you directly. Okay. So with this, I will end today's session. And thanks a lot for joining and keeping a very interactive session throughout the whole evening. Very happy to be a part of it. And thank you to the organization team also at PCCOE for allowing us this opportunity.
కెమెరాలు యాప్ బంద్ అయిపోతుందంట కెమెరాలు
Okay.
ఫ్రంట్ కెమెరా ఆఫ్ అయిపోతుంది
Okay, ma'am. Over to you, ma'am.
Hello.
Yes.
Talk with organizer, sir. May I talk with the organizer, please?
Yes, sir.
Okay, sir. I will drop off then from my end. Okay.
Yes, sir.
May I talk with the organizer, please?
Sir, just a second, sir. Yeah, we'll talk. Just a second, sir. So, it's been an enriching experience, sir. Uh, on behalf of organizing team, I think someone's mic is not on mute. Yeah. Yes. So, on behalf of organizing team, Department of Mechanical Engineering, PCCOE Pune, I extend my heartfelt thanks to our esteemed speaker, Dr. Devanand Singh sir, for sharing his profound knowledge on EV dynamics. I think now participants have more insights on the and more clarity on the simulating topic. So thank you once again, sir. Thank you once again, sir, for
Thank you once again. Thank
yeah,
you, sir.
your valuable time and taking time after your busy schedule. And we look forward for more such opportunities in the future, sir. Yeah.
Sure, sir. Yeah. Thank you very
Thank you
much.
so much, sir.
Yes. Yes.
Hello, participants.
Yes, sir, can you stop
Feedback,
sharing the screen? Yeah, I want to share the screen.
feedback link is already shared here in chat box. Kindly fill it immediately.
Yeah, interestingly, my screen is not shared anymore. It shows. I will stop. Okay. Sorry. Yeah, I've stopped. Yeah. Thank you.
Yeah, thank you,
Hello,
sir.
sir.
Thank you, sir. Yeah.
May I talk with the organizer, please?
Yes, sir, please go ahead.
Sir, actually, sir, unfortunately, my audio was not working. Just now it started to work. Can you share the link of video, sir? The presentation was very good. The link, if you share, so that we can see the links also, sir.
Yes, sir. Surely, we are planning to share all the videos. So shortly, you'll be notified on the WhatsApp group.
Okay, thank you, sir. Thank you very much.
Yeah. Okay, so participant, tomorrow again we have two wonderful sessions by Dr. Satyam Panchal. Session number one is advanced battery management for fast charging, and second session is introduction to EV and modeling. So both are very powerful sessions. So we are expecting timely attendance from you. And
Sir,
yes,
good evening, sir.
yes,
Yeah, can you please send yesterday's also PPTs?
yeah, madam. Yeah, we'll share.
Means actually you said in the chat box that it will be sent by 30th, but
Yeah.
if you send before, it will be useful for the exam, no, sir.
Yes, madam. We will notify on the WhatsApp group and we'll try to send all the data as early as possible.
Okay, we can revise the same, no? That's why.
Yes, ma'am. Yes, yes.
Okay, thank you, sir. It was very important sessions.
Yes, sir. Thank you.
Thank you.
So thank you all the participants for the huge response, active involvement and support throughout these sessions. Thank you very much. And with this, we'll end today's session and we'll meet tomorrow sharp 6 p.m. All the participants, link for feedback session 2 is in the chat box. Please start filling the feedback. The link will be open for next 10 minutes. I'll repeat, link for this session is in the feedback. You can start filling the feedback, those who have not filled. The link is shared multiple times, so you can start filling the feedback forms. The meet will be open for next 10 minutes, so you are expected to fill the feedback form. Link will not be shared in the WhatsApp group. Please ensure that you'll be filling the feedback form in the next 10 minutes.
Thank you, Prof. Thank you. Hello, sir. Hello, sir.
Hello. Dear participant, kindly fill your attendance.
Where is attendance link?
I have shared it in chat box. Please check in chat box.
Can you share it once again? We are not getting it because multiple feedback links are there, so that's why it's difficult to
There
find
is one
attendance link.
feedback link that I have shared multiple times. So please check now in your chat box. Check now. Check now.
Sir, can you please share once again?
Check now. I have shared it again.
Hello, sir. Share the slide with us,
Check
sir.
it now. I have shared 3-4 times. Devendra sir, check it now. No participant, we are going to stop now.
Shrey sir, I think we can close it. It's almost 10 minutes extra.
हेलो विवेकानंद सर। हेलो, हाँ राज सर बोल रहा हूँ सर, क्लोज कर दो मीटिंग।
Yes sir, yes sir.
हेलो सर, अटेंडेंस लिंक और फीडबैक लिंक सेम ही है क्या?
Attendance link, feedback link, same here sir, same.
Okay, okay.
क्लोज कर दो सर।
Shrey sir, we will stop it.
ओके सर, ओके, अभी क्लोज करता हूँ सर।
Close it.